A company's data can be its most valuable asset, but only if the data are usable and can be understood in such a way that it provides insight and improves performance. Data analytics is used to provide that insight. Now, there are 4 types of data analytics. The first is descriptive. It answers the question, what is or what was? Now, let's assume that we want to analyze last year's sales. We could use descriptive statistics to give us an average and range of our sales over the past year. Descriptive statistics is a great place to start when analyzing new data. It's the basis of exploratory data analysis. By establishing a baseline expectation of our data, it's easier for us to identify outliers and anomalies that may require further analysis. Diagnostic analytics answers the question, why did this happen? For instance, if we've noticed a negative trend in sales, or maybe we just had a really bad month, we could use diagnostic analytics to try and determine why that happened. We might find out that we had increased competition or that poor weather hurt our sales. If we can determine what factors influenced sales in the past and get a good understanding of these variables, we may be able to forecast what will happen in the future. And this is called predictive analytics. This is where it gets fun. We can start to think about how, whether we change advertising or sales price or any number of factors, we may be able to help or hurt future performance. Now finally, we've got prescriptive analytics. The goal of prescriptive analytics is to provide advice or recommendations about what we should do. Now think of a doctor writing a prescription, right? The doctor tells us how many pills we should take when. Same thing with prescriptive analytics. Let's think about how advertising may affect our sales. If we have too little advertising, our customers won't know who we are. Too much advertising can also hurt our company because of diminishing returns on those advertising dollars. Prescriptive analytics helps us determine the optimal amount of advertising that we should purchase in order to maximize our profits. Now, there are many analytical models, tools, and techniques. I think it will be easier to understand them if we see them rather than simply hear about them. So let's take a look at some data. So here we've got some data from a company that provides lumber to local craftsmen who make custom furniture. Now let's assume this company has had some trouble collecting payments from these craftsmen in the past and wants to be more careful about who they do business with. So how do we know who's going to pay us and who's not? The company's decided to analyze credit scores to see if there's a relationship between these scores and on-time payments. So we've got credit scores on this axis here and payments on the y-axis. Now, we're going to talk about several analytical techniques here. The first is clustering. Clustering is where we group similar objects together. The goal is that all objects within a group are very similar and between groups are very dissimilar. When clustering, we typically don't start out with predefined groups. We let the data determine how we categorize these objects. Now it looks here, if we're just looking through the data, we're going to try to draw circles around where the clusters are, right? So maybe there's one here. I see another cluster here, another one here, and then there's this kind of crazy cluster up there. Now this is a good example of exploratory analysis. So by trying to understand our data, we can visualize it, we can quickly find out that there's this specific group up here that just seems a little bit odd. This group of craftsmen has low credit scores, but are very good at paying their bills on time. And it would probably be a good idea to follow up on this group and do some additional analysis to try and determine what makes them different. All right, so this is clustering. Now let's talk about classification. Classification is another data analytic technique, which attempts to predict which category objects belong to. So in this case, if you're the lumber company, what do you want to know? Well, I want to know who's going to pay their bill on time and who's not. So we're going to try to classify these groups based on credit score, right? So maybe right here, right at 550, I think these guys are good. They're going to pay their bills, and these guys are bad, right? Now I can classify this into 2 groups. I might use more groups. I might drill down further, find some other variables. I still can't explain these guys up here, so I might have to change my classification technique in order to somehow get these guys over on the good side. All right, now let's talk regression. Regression is a powerful analytical method that looks at the correlation between dependent variables and independent variables. We're essentially trying to determine cause-effect relationships. So if we believe that credit scores influence on-time payment percentage, credit score is the independent variable, and on-time payment is the dependent variable, right? Cause and effect. Okay, now, linear regression is a common regression we typically use to try to fit a line to our data such that we minimize the space between our data points and the line. Now, luckily, we don't have to do this by hand anymore to try to figure out where this line should be. It can be done by any number of software programs, and these programs will produce output that looks something like this. All right, so let me explain what we're looking at in this output. First, we've got R. This is known as the correlation coefficient. It ranges from -1 to +1. -1 means that the variables are perfectly negatively correlated, right? So if the independent variable goes up, the dependent variable goes down. +1 means they're perfectly positively correlated. And you can see here that we've got a pretty positive correlation, pretty strong, 0.78. R squared is the coefficient of determination. It tells us what % of the variation in our dependent variable, which is on-time payments, is caused by the variation in our independent variable, or credit score. It's generally better to use the adjusted R squared number here because it controls for the number of independent variables we've included in the model. In this case, our R squared gives us some idea of the goodness of fit of the model. Now, goodness of fit tells us how well the model, which is essentially our line, fit our data. The closer that these points are to the line, the better our fit is. Now here, we've got model significance. This is a tiny, tiny number, obviously. That's what this E-22 means. This means that our model is significant. We're explaining this data. Smaller is better. In academic circles, we're typically happy with a value of less than 0.1 or 0.05. We see similar significant measurements here, these p-values. Anything less than 0.1, 0.05, we should be pretty happy with. And these tell us that our intercept is significant, and our credit score, which is our independent variable, is also significant. The coefficient of the estimates here tell us the effect size we have. So we believe that -29.4 is our intercept. Now this doesn't mean much for us here because this particular score can't go below 350. But if we were to draw this thing out all the way to 0, this line would cross at -29.4. Now how sure are we that -29.4 is the right number? Not at all, right? This is still guesswork. It's a model. We're trying to figure this out, but we don't know everything. We can be sure that we're wrong. As you see, very few of these points on our graph are actually on this line. So the chances are that at any given point, we're going to be off by some amount. The standard error tells us, or gives us some idea of how far off we are going to be. Okay? Based on statistics, we can say with 95% confidence that our estimate is going to lie within the range of approximately 2 standard errors above and below our estimated coefficient. All right, so let's walk through an example here. If we take our intercept, our coefficient is -29.4. If we were to add 2 times our standard error, right, so that's 14.5, or subtract 2 times the standard error, we're going to come up with this confidence interval. We think we can say 95% confidence interval that the intercept is going to lie between -44 and -15. Now let's look at the credit score. This is really what we're after, right? We had this idea that by using credit score, we can determine who's going to pay us on time and who won't. This coefficient here tells us that each point of a credit score increases the on-time percentage by 0.16%. So 100 points, that's 16% higher on-time payment percentage. We can use this to predict, right? Once we understand all these variables, we can use predictive analytics to figure out, let's say we have a new prospective customer. We know this customer's his credit score is 750. how likely is it that he will pay us on time? Well, based on our model, it should be 91.27%. If we go over to 750 up here, the line will hit at 91.27. And once we have this set up, it's a very simple formula, just our intercept times our credit score here times the coefficient here, we get our estimate. So if we plug in a new number, let's say 400, that drops down to 34.95%. Right? We can find this point on this line. All right, now let's walk through another example. Let's look at a call center example. Let's assume that we run this customer service call center. People buy products, but they can't put things together or they need technical support, and they call us. Now let's assume we have 12 departments here, and these are the number of service calls that each department has last month, and these are their total costs. And we're trying to understand how these service calls will affect the total cost of each department. So if we put all of this into a linear regression, we get this output. And let's just look at it, right? Let's analyze this output like we did with the last problem. Our adjusted R squared, 63%. So our number of service calls is explaining 63% of the variation in our total cost. That's pretty good. Our model is significant, right? We have a small p-value here. It looks like our intercept and our service call significance for the intercept and this independent variable are both significant. So these variables, it's a good idea to keep them in the model. And we're going to use this to try to fit the data to our line. Now, this is a basic cost function we use in managerial accounting all the time. Our total cost equal our fixed cost, which is our intercept. This is the amount of cost we would have if we have 0 service calls, right? That's where it would cross the x-axis. We're going to take our fixed costs plus our variable costs plus or times the number of units, or in this case, the number of service calls. So the intercept, we believe that even if we had 0 service calls, our fixed costs are going to be $10,732 every month. And each service call will cost us approximately $26. Now, how sure are we of these numbers? We can't be sure. We can't be absolutely sure. But if we look at the confidence interval, we've got a pretty good spread on the intercept. The fixed costs are somewhere between $6,700 and $14,750. And each call is going to cost us between $13 and $39. And we can use this information to predict what a department's cost should be if they have a certain number of calls, whether it's the same department next month or a new department that's handling a different number of calls. So let's just plug it in here. So let's say we have 400 calls. Now, what should the total cost be for a department with 400 calls? We're going to take the fixed costs plus the number of service calls times each one costs us about $26. So we can use this regression to estimate what the cost should be for a department with 400 calls. It should be $21,132.94. Now this is an example of a simple regression, right? We have a single independent variable. That's what simple regression is. Multiple regression looks at multiple independent variables. Same, very similar output. I'll show you what it looks like. It's basically the same process, but we're just adding multiple independent variables. Now, why would we do this? Let's assume that we're not happy with this adjusted R squared, right? It explains 63% of the variance. So there's other factors out there that are influencing the total cost of each department. Well, what are they? Let's assume that we've determined that one of these costs, or one of these factors that drives the cost, is the number of new products that we have to handle, right? So a new product goes out, we're going to get more calls about this new product, which means I have to train my employees to know how to deal with these new products, and that's going to increase the cost. So if we throw this information, now this is a multiple regression, we're going to throw this into our regression model, come up with this output, and let's analyze our data, right? Just like last time. So last time we explained 63% of the variance. We're closer to 80%, right? So it's a better model. Now let's check our significance of the model. We have a small p-value, so we're confident this is a good model. Let's look at our intercept, our fixed costs, service calls, and now we have this new independent variable, new products. P-value on all of these variables are very low, which is good. And now we can use this information because it's a better model, hopefully we'll come up with better predictions. So let's give it a try. So we know that our fixed costs, I guess we should plug this in. Let's say we're going to have a new department, 400 service calls, and 20 new products. What is that likely to cost us? Well, we've got our intercept, our fixed costs, plus each service call costs us $21.47, plus each new product we estimate costs us almost $286. So our estimate, best estimate based on our information, based on this data we already have, is that a department with 400 service calls and 20 new products should cost us $21,490.84. Now, how sure are we of this number? Well, we've got these ranges, so we know we're going to be off, but the smaller these ranges are, the more confident we can be that we have meaningful data here, that this model means something, that we can use it to analyze future performance or the performance of another department, to identify high-performing departments and low-performing departments, departments that are spending too much money or that are doing very well. Now, one of the problems we face with using this type of output, this type of analysis, has to do with extrapolation, right? So I think I'm pretty confident with my guess here based on a department of 400 service calls and 20 new products. But what if we extrapolate to a scenario we've never seen before, right? How confident would I be for a department that has 600 service calls? Well, this model is based on departments that have service calls ranging from 122 to 498. Once we get outside that range, we're going to lose some confidence in our ability to predict what's going to happen under these settings, right? So I don't know. I would feel less confident about a department, estimating the cost of a department with 600 service calls than 400 service calls, because this is outside of the range used to come up with this model. What about 6,000 service calls, right? How confident would I be with that? Not at all confident, because there's bound to be some other factors that I haven't encountered in my current setting, right, in these 12 departments. Once I take that many calls, I might need a bigger building. There's bound to be more fixed costs and some other factors that I can't even think of. So once we extrapolate beyond the data that we've used to create the model, we're going to lose some ability to predict the future. Another challenge we face with data analytics is interpreting our results. Regression doesn't tell us cause and effect. Now, we're trying to create cause and effect relationships or identify them and put them in as independent variables, but regression only tells us about correlation. I once heard a story about a store manager who discovered through data analytics that people who use large shopping carts buy more groceries than people who use small shopping carts. The manager thought this provided great insight. He decided to get rid of all the small baskets and carts and make sure that each customer had a large cart. And as you can imagine, sales didn't improve after the change. This manager mixed up cause and effect. Larger carts don't lead to more sales. People already know what they want to buy when they go to the store, and if they need to buy a lot, they get a big cart. Here's another example. There is actually a very strong correlation between the number of churches in a town and the number of bars in a town. Now, which is the cause and which is the effect? Do we go to church because we feel bad about what we said while we were under the influence of alcohol? Or does religion lead us to the bottle? Regression can't tell us the answer. It turns out that neither is correct. Both of these factors are caused by population. Larger towns have more churches and they have more bars. Now let's talk briefly about time series analysis. Regression often looks across different objects at a given point in time. Time series analysis is similar, but it looks at a single object across time. So again, if we're trying to map sales and chart our data across time, we might get something like this. Now we can draw a straight line using linear regression across this data, but if we're accounting for changes over time, we would probably need a non-linear function. Time series analysis can improve our predictive ability with data that move across time. There are several patterns we want to look for in time series analysis. Here we can see a systematic positive trend over time. Here's another set of data, right? Time series analysis can also show us seasonal trends. Ice cream sales probably look something like this, where sales increase in the summer and decrease as the weather gets cooler. We may see cyclical trends where data don't line up with seasons, but they do line up with expansions or recessions in the economy, these macroeconomic events. We may also see irregular trends that don't line up with the economy or the season. This might be chainsaw sales in Florida, right, where we have spikes every time a large storm blows over the state. Regression and time series analyses aren't the only predictive tools that we have at our disposal. Let's chat about a couple of others. So let's assume we've started a food truck company. We've currently got 5 trucks out in the field. Last year, we made $122,000 profit. What we're going to look at in this example is sensitivity analysis. Sensitivity analysis allows us to see what might happen in the future by changing any variables we choose. For this example, let's assume we want to see what sales or profit will be if we have a decrease in 10%, 5%, or an increase of 5 or 10% in our sales. So I'm going to drag this over. Formulas are already in there. Populate this very quickly. Oh, it even copied my line here. So we can see that what the profit will be under all these various assumptions, right? If we believe that sales can decrease or increase by 10%, we can expect that our profit is going to be somewhere between $99,800 and $144,200. Now, sensitivity analysis has its drawbacks. Our estimates are only as good as our inputs or our assumptions, right? There's a lot of things that we're holding constant in this analysis. We're going to assume that variable costs are always 60%, fixed costs are fixed at $100,000, and there's no other costs. There's no unforeseen circumstances, right? And we know that that's unlikely to be the case. Let's look at something else we can use with this graph, and that is something called goal seek, right? So what if we want to make $175,000 in profits? We're saving up for something big. That's how much we need. I want to make $175,000 next year. How much do sales have to increase by in order to make $175,000? So what we're going to do is copy over these numbers. Okay. And we are going to assume that all the assumptions hold, and what we want to figure out is this percentage here. How much do we need to make in order to come up in sales, in order to come up with $175,000 in profit? So we go to data, what if analysis, goal seek, and I want to set this cell to my desired profit level, $175,000, by changing this percentage. It's going to start at a number, and it's going to increase or decrease that number until this sheet populates $175,000 as my profit. I push enter here, and it turns out the magic number is 24%. If I can increase my sales by 24%, then based on my assumptions, my profit will be $175,000. So let's take a look at one other data analytic tool. Here I've built a very basic Monte Carlo simulation. A Monte Carlo simulation is a way to generate probabilities based on random numbers. Now let's compare it with the sensitivity analysis we just did. So on the last page, we assume that sales were moving uniformly up or down. In this example, we're going to allow each truck to move individually. Now we can still do this with sensitivity analysis. That's not what makes Monte Carlo simulation a Monte Carlo simulation. What Monte Carlo simulation does is it allows randomness to influence our profit function here. So I've determined that truck 1 the sales for truck 1 may drop 10% or it may increase by 10%. And this random function will pick a number between -10 and +10. And each number is just as likely to be selected as the other. Now, that's a uniform distribution. That might not be the best distribution, but this is a simplified example, and so that's what I'm using. It may be that we want to use a bell curve or some other distribution, but every number within this range is going to have an equal chance of being selected. Truck 2, we can see, is doing a little bit better than truck 1, and we think that the downside there is they may drop 5% in sales, but it could be as high as 20%. Truck 3 and truck 4, they're doing really well. The route must be better, the food must be better, it's barbecue, it's grilled cheese, it's something people are eating. Truck 5, we don't have high hopes for. It might increase by 10%. It might drop by 30%. It's probably some kale quinoa blend of some kind of smoothie that no one likes. So we don't have high hopes for that. All right, so what we're doing here with the Monte Carlo simulation is allowing every single number to be randomly generated. And we can do this over and over again, right? Based on these random numbers, we plug everything in, and we might make 151,000. Or under a different random set of assumptions, based on these sales figures, it might be 157 or 150, right? We can do this over and over again. Here I've done this 200 times, okay? 200 separate times. And what we can do when we build all this out, and you might use more than 200. You can go thousands if you want. We can then figure out what our average is by looking at all of these random probabilities or random trials, putting it in some kind of a function to figure out what the average is. And so we have a guess, hey, you know what? My coefficient estimate is 151,989. We can also generate a confidence interval by stacking these from the highest to the lowest and taking the middle 90%, right? So since we have 200 trials, we're going to take 10 trials, or 5%, below the middle 90%, and 5% or 10 trials above, right? So really you just need to know the confidence interval. We think that this is our best guess, but we're 90% confidence based on our assumptions that our profit is going to be between $140,044 and $163,284. Now, just like with our sensitivity analysis, there are some drawbacks here. We can only be as confident in our estimate as we are in the assumptions used to build out this model. So I hope this provides you with a good overview of data analytics. Data analytics can be very difficult at times. It's sometimes difficult to deal with massive quantities of data. And data are often in formats that must be cleaned before we can perform any of the data analyses that we just saw. But the benefits of data analytics are worth dealing with these challenges. Employees who understand how environmental factors, employee factors, and customer factors influence company outcomes will quickly find that they can add tremendous value to their organizations.